All right, now I think we're back. All right, sorry for the delay. It takes me too long to get set up, and this computer is too slow. All right, so let's look at our next section. So I kind of want to do, actually, let's go to naming. Let's just name first, and then we'll get into all the compounds and Lewis dot structures and geometry. And so let's finish up naming covalent compounds. And so I think naming covalent compounds is kind of easier in some sense. And so they give us this introduction. And so basically, right, they say, well, the formula cannot be readily determined since you can have different combinations. And so let's just take nitrogen and oxygen for an example. So we can't just say, you know, nitrogen oxide because there's too many different combinations, right? There's NO, NO2, N2O, N2O3, N2O4, N2O5. And so how do you distinguish between all of those different combinations? And so this is also just for molecular compounds with two different nonmetals, so right, just like binary molecular compounds, so not naming anything more complicated since the naming gets much more complex. And so usually you write the name of the element with your smallest group number first, and then you use prefixes, and this is the important part, is instead we have prefixes to indicate how many atoms. And so similar prefixes to your hydrate portion, so mono, di, tri, tetrapenta, hexa, hepta, octa, nona, deca, and of course can continue theoretically for other combinations. And then if you have the first element, if it's just a 1, then that mono is usually omitted. So we could go back to all those NO compounds and write out their names, right? So NO, so that one is nitrogen monoxide. And then NO2, so now nitrogen dioxide. And then N2O, so now dinitrogen, since we have 2, monoxide. And we'll just do this last one, so N2O3, right, so dinitrogen trioxide. So kind of so forth. And I'm pretty lenient about the spelling. Luckily, y'all are all taking this class in person because sometimes I teach this class online or hybrid. And then I have to tell people if you misspell stuff on the exam, just let me know because, you know, auto-graded. But I'm not too picky because the vowels can get kind of confusing. All right, try these 3 for practice. So take a minute or so and then we'll go over them.
Is that NL3 or NI3?
I. So let's try them. What do we get for A? What do we get? Shelby?
Is it mononitrogen trioxide?
So we can leave off the mono, but the rest is good. So then the nitrogen triiodide, and I think that one has 2, so iodide. So it ends up with 2 I's. Looks kind of funny. And then, yeah, just ending is still "ide." So just remember that. What do we get for B?
Phosphorus pentachloride?
Yeah, phosphorus pentachloride. And then the last one,
Tetraphosphorus? And then decasulfide?
excellent, tetraphos or deca.
Can you go back up to the little chart that you had, like the, that printer? Thank you.
Yep. And then, so the other little thing that we should go over before we jump into structures is just how to get the mass. And you may have figured this out already in your labs. But basically, right, if we go back to our molecular weight here, this is both the molecular weight of one atom, right? So this could be 11.811 atomic mass units if we're talking about one boron. Or it's the molar mass, so 10.8 grams per mole. And so then if we want to find the mass, so let's just do water. We'll walk through this one and then we'll try another. And so notice, right, they just add up everything. And then you can always have different answers, right, with rounding. And so in this case, they rounded the mass of hydrogen to 1.01. You know, some people just round it to 1. Some people use 1.008. So there's going to be, you know, different answers. So just be cognizant of that. You know, I'm aware of that, so I know your answer could have some fluctuations with rounding. And then 2 hydrogens, so multiplied times 2. And then plus 16 for the weight of oxygen, which is, again, a rounded value. So you could use 15.999. So those are the 2 common ones. And then add those up to get your total mass. So either one molecule is 18 atomic mass units or 1 mole of water is 18 grams per mole. All right, so now add that up. Let's just try silicon tetrachloride here and see if you can get the mass of that one. let's see, what do we get for this one? So what did you find the mass of silicon was?
169.898.
Oh, that sounds like the total, so 169.
Oh, sorry.
Oh, you're fine. 169 point what? 898 you said?
898.
898. So from memory, that sounds good. So is that what other people got?
I got 170.1. Is that
Oh,
really different?
yeah, so 170, right? That's really close. So that's fine with rounding. So yeah, roughly, 28 grams per mole for silicon or so. And then chlorine, right, is what, 35.45 times 4. And so that should give you that number. Any questions on that? And of course, right, all the masses are found there. And so, right, some discrepancies with rounding is to be expected. Questions on how you find the mass of anything? Yeah. So, right, there's going to be rounding, so that's fine. Like if you got 170, don't worry about it, because I don't know what numbers you're pulling from. You can round differently, right? You could round it to 28 and then just get 170. You could report to 1 after or 3 after. It all depends on what numbers you choose. No, I'm not going to be that. Right? There's like no way that I could be that picky. That would just be like insane. Yeah. So then it depends, like it would depend more on what the problem is given. So right, usually how these problems will work is like, oh, we have 5.00 grams of silicon tetrachloride, right? How many moles? And well, I won't go there today because that's another chapter. But then you're just looking at these sig figs, right? So then I'm not going to worry about what you found for your mass, for your sig figs, right? It's just dependent upon the 3 here. Does that make sense? Yeah. And like probably ideally, you want your mass to have at least as many sig figs as you were given in the problem. But again, I'm not going to be like that picky about it. We're not that precise right now with our values. And that being said, so like, oh, what if you did really, really want to know accurately your mass? What you actually have to use is like I would suggest some sort of CHEM drawing software. Unfortunately, I don't have it on this computer because you have to have a license or, sneak around it, which I haven't done on this computer. But like ChemDraw, for instance, ChemDraw can give you a much more accurate mass because the problem is that you get into isotopic patterns as well. And not to go too far down the rabbit hole, but ChemDraw would give you like the isotopic pattern as well. So like every mass that you expect for the different like potential isotopes as well. So I'll say more accurate and gives isotopic distribution. But that's kind of a little beyond this course, right? We don't care about that level of accuracy. That doesn't really matter to us right now. We just need a general rounded mass. So yeah, as long as you're somewhere in the ballpark of 170, you're fine. All right, so now let's go towards our last section. So we'll kind of see what types of compounds these groups like to make, and we'll look at the geometries, and then we'll do the geometries with our groups. So we'll kind of go back and forth. And so you should pick up the Vesper handout if you haven't already. Anybody need it? All right. So that'll be a good kind of cheat sheet. But let's start looking at just the patterns first before we dive too much into our cheat sheet. And so let's look at group 4 compounds. And so before we dive into group 4, let's talk about your homework a little bit because you had to draw some Lewis dot structures. And so let's first say, so we have our Lewis dot structures. And so let's look at, and so if we look at our periodic table, we have carbon, and carbon is actually an exception, so we'll look at that in just a second. But let's look at our Lewis dot structure for like silicon and germanium and tin, lead. And so this would be relevant. And so the Lewis dot structure for those should have come out with 2 dots on one side, right, filling up that s orbital, and then 1 dot on the others, so 1, 2. And so I just want to emphasize that there is actually evidence for that they can make stable 2-coordinate compounds. So silanes are a lot more reactive, so they're harder to isolate. But germanium is known as a 2-coordinate compound. So it's a germanium chloride, and it has 2 little electrons there. It's technically stabilized by dioxane, so that helps to give it some stability, but still 2-coordinate compound. And so now let's look at the exception. And so carbon, its Lewis dot structure is generally accepted as 1 dot on each side. And so why that is because carbon has a much greater tendency to what's called sp3 hybridize. And let's see, I'll try not to get too excited because I get excited. And so essentially, if we just kind of visually think about that, what's happening. So sp3 hybridization. So as you can kind of tell from this, so this is saying we're taking our s orbital and then our 3 p's and then making 4 equal but different looking orbitals. And so what I mean by that is, again, we're just taking a visual approach. So you could also take a mathematical approach, but that's beyond the scope of this course and also the next course. And so we can just take our kind of p orbitals and think about them. So px, py, pz, and then also our s. And so basically, if you could combine them mathematically and redistribute them, you would get your tetrahedral geometry there. So there's my sp3 hybridized lobes. And again, I apologize, I'm not much of an artist, but we can tell we put in 4 orbitals, so 1s, 3 p's, and then we got our 4 little lobes here for bonding. And then that being said, many of the other compounds also still like to do this 4-coordinate thing as well. And so some representative compounds. And so the classic one is methane. And so we can draw that out. And so just kind of distributing them evenly. And I try to show 3D character. So this fat wedge means that it's coming out of the plane of the board. The dashes means it's going behind the plane of the board. And then these are in the plane. And so then we could look at our compound chem sheet there, our VSEPR chart, and kind of at least start to relate that. Sorry, let me get a digital copy. And so if we're looking at this compound chem thing, so it has some numbers on the side. And so these numbers are electron pairs is what they calls them. So that's either lone pairs that are on the central atom or substituents. So looking at methane, right, we have 1 central atom, and then it has 4 things attached to it, so 4 hydrogens, 4 atoms. And so then we know it's in electron group 4 here. And then if you've noticed, right, so if we go on over, if I could zoom in better. So now the first geometry is shown tetrahedral here, and right, it's going and distributing those atoms, right, all evenly around. So this is basically right there, most spread apart, fully symmetric rearrangement. We could bust out the molecule kits to help us as well, but this also shows that geometry. And so I would note that as the geometry, so that's pretty common, this tetrahedral geometry. And so let's look at kind of other group 4 compounds. So right, so all the other group 4s kind of tend to do similar things. So we have like silicon tetrachloride, germanium tetrachloride, so those would all be similar structures. And you could substitute, right, fluoride, bromide, whatever. So lots of different permutations, hydrides, etc. So that's kind of group 4, at least summarized. We'll get some other stuff. And so now if we go to group 5, so now we're looking at nitrogen and phosphorus. And so do you remember how many bonds they like to make for like nitrogen? Yeah, triple bonds. So they want to make 3 bonds. So triple bond with itself, or up to 3 bonds here, but then we'll also see where it can do some expanded stuff. And so nitrogen, kind of the classic compound is ammonia, NH3. And so phosphine is also similar, so like PH3, so this is nice and reactive. So PCl3. And so these phosphines tend to be pretty nasty compounds, right? So that's phosphine, so that'll ignite in air. This also ignites and smokes in air. I should have also mentioned that silicon tetrachloride ignites and smokes in air and is pretty angry. Also was used in times of war. I'll add to this. So these 2 compounds are quite fun in terms of they used to be used in war. So this is affectionately known as tickle. I don't know why, but it's freaking ignites. and chemists call it tickle, but that's a chemist's sense of humor for you. But the significance of both of these historically is that, like I mentioned, they've been used in war, so they immediately react with the atmosphere to create chlorine, like HCl gas, so, acid. And then also kind of a smoke screen effect, because you can make silicon dioxide as well, or titanium dioxide, so both of those. So titanium dioxide is white and generally used in sunscreen. It's also gotten famous because they've pointed it out that it's in like Skittles and like other things. They're calling it toxic now. I thought it was safe, at least. That's what I learned, that titanium dioxide is safe and used in water purification. Now they're saying it's like not safe and it's in your Skittles.
Well, they're like, by the way, this causes cancer. You're like, add it to the list.
Yeah, I mean, it's like, what doesn't cause cancer? But yeah, it's also titanium dioxide. I don't know if any of y'all are vegan or eat like vegan cream cheese, but they make it white with titanium dioxide. So anyways, yeah, used in war. So sometimes if you look at old footages, the airplanes are like dropping vats of either silicon dioxide or tickle, and it's just creating a horrible smoke screen of acid and smoke. So anyways, that was fun. So moving on to more compounds that are angry. So see if you can draw the Lewis dot structure for one of these. So it doesn't really matter which one because they're all similar. But just see if you can draw it for a second. And so hopefully you got something that looks like this. And it doesn't matter what atom you put there. So, right, could be chlorine, could be fluorine, bromine, all those would have similar patterns. And so now let's look at this geometry and how to analyze this. And so now we're still in group 4 actually. So we have 3 atoms and then 1 lone pair. So four things attached. So we can go back to our sheet. So 4 electron pairs. And then, right, we're not tetrahedral since we don't have 4 atoms anymore. And then so we go on over, and then it even kind of spells it out to help you. So it says 3 bonding pairs, so that's what the BP stands for. And then 1 lone pair for a lone pair of electrons. And so now what's the geometry of our ammonia? So what does it say? Yep, so trigonal, pyramidal, or pyramidal, however you want to pronounce that. So basically, right, kind of looks like a pyramid shape too, with these little substituents, right? And so maybe I should have brought the molecule kit, but it's just kind of like that. So we're just looking at our ammonia shape, and so let's write it down. So trigonal, pyramidal. And so write PCl3 and phosphine, so those would have the same geometry. So now let's look at other compounds. And so I'm going to skip down to this expanded octet. And so your book, and lots of textbooks, and maybe even you learned this in high school, but they make some sort of like comment, and it always goes, oh, we can only have expanded octets after the 3rd row. And usually they say something like, oh, that's because we're using d orbitals. But the thing that I want you to know is that there are absolutely no d orbitals invoked. So we're going to draw out, so PCl5, so again, nitrogen can't do this, not because of a d orbital argument, but it's actually just too crowded. And so what I mean by that is if we were to take like the analogous compound nitrogen pentafluoride, they found that it can't exist because there's just not enough room. And so, right, it would have to look something like this, so drawing our geometry. So this is still the geometry of PCl3, and so I should add, right, theoretical. And so they found, using calculations, that basically these fluorines here would have to be extra elongated to fit around. So they're just, it's physically too small. So you just physically cannot fit the fluorines around it. But it has absolutely nothing to do with the d orbitals. And if you want me to prove it, I will, after class, I could go crazy and draw an MO diagram. Otherwise, you'll have to just accept that. And so phosphorus, arsenic, and antimony can all do these expanded octets, and bismuth as well, so all these, so just not nitrogen. And so here's PCl5. So that's fun. And then I don't think y'all need to know the geometry. Yeah, so for your class, what's kind of nice for y'all is I have kind of the key geometries on the next page, and we'll kind of, again, go over your classic examples. But for our purposes, I'm only focusing on the trigonal planar, tetrahedral, and trigonal pyramidal and bent geometries. But I'll still kind of show you at least how to use the chart. And so write PCl5, we go back to our chart. We have 5 things attached to it, and then write 5 atoms. So then it would be trigonal bipyramidal, since it looks like 2 pyramids. You could put one and then the other one. let's see. Oh, I skipped. Let's add in group 3, since there are some funny ones in there. And so group 3 are kind of odd. We started talking about them, so kind of like the aluminum trichloride, right? It's like they act like a metal plus a nonmetal, at least in name or in theory, but then tend to behave like covalent compounds. So this is covalent. So same thing, if we look at boron, so boron makes a bunch of covalent compounds. And so for our purposes, we'll focus on like the simpler ones, so like BF3, or again, like the aluminum. And so those make our trigonal planar complexes. I keep changing. So again, doesn't matter what the halogen is. And then, so the other thing is we kind of want to get a sense of their reactivity as we draw them and think about how they behave, why they behave that way. And so I'll tell you that group 3 compounds, they're all angry and fuming. So BF3 is an angry fuming liquid, and then aluminum trichloride is an angry fuming powder. And so we can think as to why that is. And so if we're looking at our Lewis dot structure, so this is a correct structure, but what's wrong with it? What's funny about it?
Does it have like the dashes and the?
So the dashes are fine, and it is planar, so that's actually okay that it doesn't have dashes. But what else is funny about it? Count your electrons too. So what do you notice? So remember, right, so this goes back to what I was saying, like, there's no wrong structure necessarily, but we need to figure out how to analyze them. And so if we look at how many electrons our boron kind of feels, so how many electrons is this? Well, 3 bonding pairs, right? But then how many total? So 6, right? And so this is weird. And so, right, we notice, well, we have 6, I'm going to call it 6 total electrons. So that means, right, that boron is feeling kind of 6 total electrons. But what was our rule again? So octet rule. So we're violating that, right? So now we can say, oh, well, this violates the octet rule. Of course, right, we don't have any other electrons, so we can't really do anything about it. Chlorine is not about to make a double bond. It's 2 electronegative, so that's not going to happen. But now we know why these compounds are angry and fuming, right? So they don't have enough electrons, and then there's water everywhere, so they're just going to go ahead and grab some water and react with oxygen. Question?
So does that make it nonpolar?
It is nonpolar, and so kind of a hint for the polarity is that you want it to be fully symmetric. And so if we go back to our little cheat sheet, so 3 electron pairs, trigonal planar, right, fully symmetric. And so my cheat is if it's in this first column here, no matter what electron pair is, it's nonpolar for sure. Because these are all, right, the fully symmetric ones, as long as it's all the same atom. And so kind of the other way to think about polarity, and let's kind of jump there. And so looking at polarity, since we're talking about it, again, let's look at our fully symmetric. Now we'll look at carbon tetrachloride. And so if you were to do this kind of more rigorous, how you do it with polarity is you want to draw an arrow kind of showing where the electrons are being pulled, And I'm doing it the chemistry convention because I think physics has opposite arrows. But I'm showing the arrow going to the electrons, right? So chlorine's electronegative, so it's being pulled that way. But then for this case, right, it's going out in all four directions evenly. So your overall vector cancels out, right? So if you've talked about vector and vector addition, this might help. Otherwise, you might be more confused. But kind of, again, the key point is you have four of the same atom, and so fully symmetric. So fully symmetric, so then we know it's nonpolar. So this is nonpolar. And then we could compare that to dichloromethane. So now dichloromethane, CH2Cl2. And so now this one, right, chlorine is much more electronegative than hydrogen. So if you were to kind of draw the vector, you would see that it's just more on one side. Or you can just kind of recognize, well, I don't have four of the same atom, or they're not like similar enough. And so, right, like carbon difluoride, dichloride would probably be more nonpolar E. But there's also going to be some gray area if we were to get like really into it. So on an exam, I probably wouldn't ask you about this just because that might create too much confusion between the fluorine-chlorine electronegativity difference. But I would consider this more nonpolar, right, since they're similar. And then this one is most certainly polar. And then, so looking at other polar molecules, so a classic polar one, so again for our trigonal pyramidal, is ammonia once again. So there's our ammonia. And so notice, right, this kind of follows with our not symmetric rule. So we don't have another hydrogen, right? We have a lone pair. So now our electron density is actually being pulled towards our lone pair. But again, our hint is that, well, this is a fully symmetric one because it's the first one. And now it's the next one, so not fully symmetric, so probably polar would be a good guess for all those. All right, so let's go back to other classic examples. And so now we have our group 6 compounds. And so those tend to make 2 bonds. So we could have, right, H2O, OF2, SO2 as well. So see if you can draw, let's try SO2 because this is a funny one. So try to draw the Lewis dot structure for SO2. So what do we get for our SO2. So how many, and don't make a triangle, I should have maybe given a hint, but. So how many lines do you have between the sulfur and the oxygen? Between both of them?
Yeah.
So let's see. So then how many total electrons do we have in the system?
Isn't there the 2 dots on top of the S though for the bonded pair?
So that's what I'm trying to figure out still. So you put 2 dots there,
Yeah.
and then filled in. So let's see. So we have, right, 6 times 3 is 18 electrons. So 1, 2, 3, 4, 5, 6.
And then the dots around the oxygen, yeah.
So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18.
Yeah.
And so this looks somewhat okay. What's wrong with this? Sorry? Oh, I meant like don't draw a bond between the 2 oxygens. So yeah, it's fine. The geometry is actually fine. There's something a little off about it.
Would you rather do a double bond between the S and O? Like
So-
double bond instead?
Yeah, that's what I would say. And so why is that? Because we got to reason out why. So what's wrong with this structure? Yeah. Or it's, yeah, so that's the big thing that's kind of, and again, I'm saying like wrong in the sense that, right, we want to make our structure, because this is a perfectly good start, right? You have your total number of electrons, and that's really the most important thing, that you have the correct number of electrons in your structure. And then you say, well, does everybody have 8 electrons? You know, can we do that? So where they're feeling 8 total electrons. And so right in this case, no, we have 6 electrons. And so then the question is, well, maybe let's make 1 double bond and see what happens. Because again, there could be more than one right answer. And so we'll kind of get into that, is that there's resonance structures. So I just moved 2 of these electrons over into a bond now. And so now let's kind of check this out. So we have 8 here, 1, 2, 3, 4, 5, 6, 7, 8 on the sulfur, and then 8 on the oxygen. And so I like this structure for now. And we have to introduce at least one more little thing to analyze these structures. And so that is formal charges. And so now let me take this. And so now let's get into what are formal charges. And so our formal charges are going to be our next step to analyze. And again, we're kind of creeping there slowly as we progress through the chapter. And so now let's say, well, what is our formal charge? And let's just look at our formula. And so that's going to be the number of electrons in our neutral, or right from periodic table. And so what I mean by that is, let's just look at sulfur for a second. So sulfur, 6 valence electrons, so that's our number that we pull. So number of electrons, maybe I should put valence electrons. And then to get our formal charge, we're going to take that number minus the number of bonds, and then minus the individual electrons. And so you might see different variations of the formula, because sometimes they say like number of lone pairs times 2. So that's why I say count the individual electrons. And so then if we analyze this for sulfur, so from our structure here, so sulfur, number of valence electrons, again, just from our periodic table, so that's 6. And then minus, so number of bonds, so it has 1, 2, 3 bonds, so minus 3. Then minus our individual electrons, so 1, 2. And so that leaves us with a positive 1 formal charge. If we look at this oxygen, so I'm going to call this oxygen number 1 for a second. So oxygen number 1, so same thing, 6 valence electrons, minus 2 bonds, minus 1, 2, 3, 4 individual electrons. So that one's 0. And then our last oxygen, so we do the same analysis, so 6 minus 1 bond minus 1, 2, 3, 4, 5, 6 electrons, and so that gives us a negative 1 charge. And so now there's a couple of things we need to know about the formal charges. So first of all, right, your formal charges should add up to the total charge of your molecule. So in this case, right, it's 0, so it should be 0. So on one hand, this is okay that they cancel out. But the other thing is that with our Lewis dot structures, we want to minimize our formal charges. And so you could say that maybe even this is not the best structure, right? Because we have a +1 formal charge and a -1 formal charge. And so you might actually want to make a bond, a second double bond. And so now redrawing it, this is kind of the better accepted structure, since now we have 0 for the formal charge on everything, so we could redo the analysis, but it'll end up being 0 on sulfur and 0 on that oxygen. And we do have, so what is our new problem though that we've created? And so now it has 10 electrons, which isn't horrible. So that goes back to expanded octets. So sulfur and phosphorus, again, tend to do like 10 or 12 with our expanded octets. So sulfur tends to do 10, or again, 12 depending. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we want to at least acknowledge that, right, we have 10 total electrons on sulfur. Just note that maybe even on an exam, you could write both and describe them. But that's kind of what I'm looking for, you know, on an exam. And I'd probably say, you know, you want to include like your relevant structures. And so these are technically called resonance structures, where they're all showing the same connectivity, right? We're just moving electrons around. And so, right, these electrons are just giving us a deeper insight to kind of their reactivity and how their bonding is. And then again, you know, you could argue more, look at the solid state and look at how it behaves to try to figure out which one is more of the true structure. But, you know, for our purposes, just being able to draw them and kind of go between them and analyze them is important. So if you were to draw this structure, it would be good to draw the formal charges for completion's sake, or otherwise, you know, you draw this structure, show it has 10 electrons, acknowledge that. Or, you know, we could even go back to this structure, right? It's not bad, it's not a bad starting point, has our total number of electrons, but then you just want to show, okay, we are missing some. We only have 6 electrons on sulfur. So that's kind of the important part, right? Is like analyzing the structure, not just like, I got the textbook answer correct. Does that kind of make sense and hopefully make you feel better about structures? All right, we're kind of running out of time, I'm just thinking what I want to say more. So group 7, right, we've generally seen that they tend to make just like one bond, at least, again, kind of normally. But I did want to mention that they can do kind of funky stuff as well. Like, for example, this is a compound, II3, I think with a negative charge on it, if I remember correctly. 7 times 3, or sorry, 7 times 4 is, maybe it doesn't have a charge. I can't remember. Okay, no charge. I can draw that quickly just so you can see. So that has 28 total electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So let me redraw that a little better. So 2 lone pairs on that iodine. And again, you don't need to know the shape of that, but just at least appreciate that they can do some funny stuff. And then group 8, right, we said that, oh, they don't really make compounds except when they do. So kind of the common ones are with argon and krypton. So either, or xenon, sorry, so usually it's xenon difluoride or xenon tetrafluoride are kind of the 2 more common ones. And that's only because, again, we go back to a size argument and then how diffuse this orbital is. So xenon, right, large orbitals, but then also big, diffuse, and so they can, bond if you force them. Same with like krypton and argon, and I think maybe neon, but it's more rare to get neon to react. So usually xenon is what you find, and then obviously chemists are always trying to make new stuff, so. And last thoughts on geometry. So trigonal planar was our BF3 or aluminum trichloride in general. And then going back to our sulfur one, so we spent a lot of time on sulfur, and then we should have concluded the geometry. So the geometry is bent for our purposes, but this is a funny one, and I wanted to point it out because most group 6 have 2 lone pairs. So if we go back to our group 6 up here, so let me redraw the definitive sulfur dioxide structure, but then we can also, of course, compare it to our other group 6s. Oh, lost its lone pair. And so your other group 6s are like water, so that has a even bent structure. So let me draw that to compare. Or OF2 looks the same. So right, H, 2 lone pairs on there. And so both of these, right, would be polar from the asymmetry as well. And then this is bent. And again, for your class, you don't need to make this distinction, but I'll point it out. And so we have your 3 electron pair. So this would be like for SO2, right, where we said it had 2 things and then 1 lone pair. So still bent. Sometimes people call this V-shaped bent. This one just calls it bent, but you might see different names. Again, for our class, we can just call it bent. And then that's compared to your 4 electron pair bent, like your water or OF2, where you have, right, 2 lone pairs instead, so different bond angle, right? So this is larger of almost 120, and then this is closer to like 104.5, so different angles, but both bent, and again, you might see the distinction that this is V-shaped bent, but not in our class. All right, I think that is hopefully a quick summary of molecular geometries and things. And so after your quiz, right, if you still have questions about the homework or drawing stuff, I'm more than happy to help. But I think for now I'll stop talking and then I'll hand out the quiz. So if people want to take a break, go ahead, take your break. But otherwise, I just want to get the quiz out in case some people want to run away. All right, now I'll stop this stream.